SSDs are key to the memories of many devices, from phones to laptops. But how do they work? Well, let us find out.
Before we understand how SSDs work, we need to understand how computers store memory. Computers store memory through numbers in the binary system. Numbers can easily represent everything, since all sensory data, videos, sound, etc. can be expressed through numbers. For example, if we had a sound, we could put the sound on a graph for the different pitches of the sound and represent those in numbers. So let's say you wanted to download an app from the internet. First, the internet would send a binary code to your laptop's processing unit. This will be processed and then redirected to your laptop's SSD. Now here, the storing begins. Solid-state drives are composed of many memory cells. In these different memory cells, there are binary digits encoded. Let's look inside one of these memory cells, also called charge trap flashes. Here we have a diagram of a charge trap. First we have the control gate. This control gate connects to three layers. The first and third layers are insulating outside layers. In between the two layers is the second layer, which is a charge trapping layer where electrons are trapped. At the bottom of these three layers, we have N-type silicon and P-type silicon.
N-type silicon is silicon doped or added with phosphorus atoms. Atoms have three main types of subatomic particles: electrons with a negative charge, protons with a positive charge, and neutrons with a neutral charge. Electrons are positioned based on a ring system. If the furthest ring from the nucleus is incomplete, the electrons in that ring are the valence electrons, which participate in the formation of bonds between atoms. Phosphorus here has 5 valence electrons, and silicon has only 4 valence electrons. Large amounts of phosphorus contain many free valence electrons for bonding. On the other hand, P-type silicon is silicon doped with boron atoms. Boron has 3 valence electrons, hence there are more holes, or places without electrons in the P-type silicon. To read the info on a charge trap, the CPU applies a voltage to the input and the control gate. Naturally, the electrons in the N-type will attempt to fill up the holes in the P-type. As they do so, they create a barrier, repelling any other electrons attempting to attract with a hole. The voltage from the control gate will break down this barrier, allowing the current from the input to freely move across the P-type and through the output, which gives a 1. However, if there are electrons in the trapping layer, the voltage from the control gate will be hindered by the negative charge from the electrons, fixing the barrier in place and thereby inhibiting the current, which gives a 0. This gives us the question: how do we write a binary value on a charge trap? To change a charge trap value from a 1 to a 0, we must apply such a strong voltage on the control gate that not only does the barrier break, but some electrons are pulled towards the trapping layer, tunneling through the second oxide layer in the process. The process of tunneling is similar to teleportation. But how do you tunnel through an object? Well, electrons are never in a well-defined position. Rather, they are at a range of positions at a given time. If an electron is being pulled somewhere, it is likely that the electron will be closer than further from the object pulling it. Because of this, the probability that the electron is above the second oxide layer is high, letting the electron tunnel through. In addition, the second oxide layer, also known as the tunnel oxide, is very thin, about 75 to 100 atoms thick. Now what if we wanted to change the direction and get a 0 to a 1? To do so, we would apply the opposite voltage on the control gate, thereby kicking out the electrons from the trapping layer and into the P-type, which gives a 1. That's it for this video. Thank you for watching. If you enjoyed this video, we think you might enjoy these 2 videos. Please subscribe and like this video. We're aiming for 50 subscribers by the end of this year. Again, thanks for watching and happy holidays. Bye!